What's up, guys? So today we're going to do the triaxial test on sand first. So it's a consolidated drained test on sand, and it's actually testing dry sand. So this is the Triaxial Cell. Basically what you'll be doing is building your sample inside this and putting it up here. And then once your sample is made, then you would need to close the system with this acrylic tube and close it up and test it. This is the material that we need for running the sand triaxial test. So first, obviously, a little bit of the same clean sand that we tested for direct shear. We have a caliper that we'll be using for measuring heights and diameters. We have some of the screws that are necessary to tighten up the cell. We have a mold that helps us prepare the sand sample. This is the loading piston with a displacement dial, which basically measures the axial strain while the test is being done. This is the top cap of the sample. I'll show how to assemble this as I'm preparing my specimen. This is a funnel to get the sand in. This is vacuum grease. It helps us seal the specimen to avoid any air going in or out from the system, other than places where we want to. These are filter papers that we would put beneath and on top of our specimen to avoid any sand moving around or outside the area of testing. These are O-rings. These are little rubber O-rings that help us seal the specimen. And this is a membrane. Basically just latex. Your sample will be going inside the membrane. So this is what that looks like. Okay, so this bottom cap has a little drain machined into it, right? This allows for that drainage, essentially in the dry sand, for air to go outside of the specimen and actually to consolidate the sand. That tube that you're seeing here is coming out through the bottom of the cell here, allowing for that drainage, right? So when we test the clay, we would take this off basically and replace it with a bottom cap that doesn't have that drainage, which would look something like this one, right? So this one doesn't have any drainage machined, right? So we've replaced this bottom cap with this bottom cap for the clay testing, which I'll show later. Alright, so the first step is to apply a little bit of vacuum grease to this bottom cap to kind of seal and airtight it for when I want to place the membrane on it. It'll be sealed. You'll see the membrane going on top of this in a second. So right now I just put a little bit of that, and I will be placing the membrane right here over this area like this. Making sure that the membrane is all tight and sealed going towards the bottom. So this is what that looks like. Then I am going to place two of the O-rings at the bottom cap. Usually how I would do the membrane is to stretch them on something like this. So this is how I would stretch. It's usually a two-man job, but I'm going to try to do it myself. These are very tight, and it's hard to stretch them sometimes, but that's how I get it on. There goes the second one. So I got 2 of my membranes on here, so I basically stretched them. Now I am going to place the membrane on the bottom cap, right, to seal the membrane. Right, so this is how I would go down, and I would try to push these down off this metal tube. So there's goes one, and that's the second one. Right, so that's what this looks like. So then I remember this was my mold. It's called a split mold, so it splits up like that. These are some lines allowing for air to be vacuumed out, and that's the little notch that it has for connecting the vacuum hose, which you'll see in a minute. So that's the assembly, and let me show you a side view of this. So this is what it would look like from this side, right? So these are handles that later on help me open up the mold after I prepare the specimen. It's supposed to have another handle here, but it's been broken off, and that's your little notch again to get connected to vacuum. So this is how I would connect the vacuum to it, right, to stretch the membrane. I'll show that in a second. So as you can see, our membrane is a little bit too tall for this mold, so I'm going to cut a little bit of it from the top. Oh, there we go. What a weird noise. Hopefully we didn't cut too much, but anyways, this is probably enough, because in the end I want to place this top cap, right, and you can see that the membrane is going above it, so we cut the right amount, no problem. Okay, so next step is to stretch the membrane over the split mold. There's one other thing that I do, and it's just stretching the membrane, so, or the O-ring. So go ahead and pull that all the way. Yeah. All right, there we go. I found this step useful to do, just to hold the split mold a little bit more firmly. So I put one of the O-rings here just to keep it tight, and you'll see when I'll be taking it off and putting it on top of the top cap again. So now is the time to basically air pluviate my sand. So same concept as before. So I have the sand, I'm going to place it all in a funnel. This is about 109 grams of soil. So I'm going to go through air pluviation, but before that I'm going to show you something else first. We have to place the filter paper at the bottom of our specimen so that none of the sand can fall out or go out. So I'm going to place that in. I actually should have done this a little bit earlier, but I missed it. So here we go. Then I'm going to try to flatten it out at the bottom of our specimen. Okay, so I have my filter paper in. Now is the time that I'm going to stretch the membrane.
Around this.
So that's how stretching the membrane looks like. And the next step is to connect this to vacuum. So I'm going to hook up our vacuum hose to this. And I'll show you in a second what this looks like, and once we start the vacuum, you'll see the stretch of the membrane. So now we have the membrane stretched, we have the vacuum hose connected to the split mold, and now is the time to apply the vacuum. So you can see the membrane being stretched. I'm going to go to -5 psi on the vacuum and keep it there while I am air pluviating the sand sample. So sometimes you get a little bit of noise because of some air. That's probably enough vacuum. We're at 5 psi. So that little whistle was due to some air getting into the system, but now that's gone. So the rest is now to air pluviate the sand. All right, guys, so now I'm ready for air pluviation. I have the sand, as you can see, in my funnel. I have one of my lab mates, or in this case, the assistant, who's going to help me prepare the sample, right? So as I'm air pluviating the sand, my assistant is going to tap on the mold a certain number of times as I'm doing this, and this is for the reason of compacting the soil to a little bit of a higher density. So that's one thing that's going to be done as I'm air pluviating. The other thing is I want to maintain a certain drop height for the sand particles. So right now you can see that the sand is going to be starting to fall from this right at the top of the mold. So as the height of the sand is rising inside the mold, I will be lifting my hand and going up to maintain a certain drop height for the sand particles, as well as the tapping. So these are things that you want to keep consistent from your first test to the second test to the third test to achieve a consistent density throughout the 3 tests. All right, so 1, 2, 3. So I'm slowly raising my hand. Maintaining the same drop height. All right, maybe just a couple more taps. So did you count the number of taps that we did?
36.
36 taps. So then we keep the remaining amount of the soil, and we weigh that amount that is now retained in the funnel to know how many grams of soil we actually put in the sample. I'm also going to collect some of these sand particles that kind of fell off here. It's really important to do that for 2 reasons. One is obviously to get the right mass that is in the sample, and 2, these sand particles get stuck when we're going to put back the cell, and we're not going to have a perfect seal, so you'll have some air going in or out of the system, and you want to avoid that. So we're going to measure the weight of the sand that was not in our sample from the 109 grams.
5.2.
5 grams?
5.2 grams.
So 5.2 of the 109 did not go into the specimen, so that leaves us with something around 104 grams being in here. So the next step is I'm just going to make the top surface flat, and once I do that, I'm going to place my, here's a top view of this, by the way. So again, the vacuum is still connected at -5 psi. That's the top of the specimen. I'm going to place this filter paper on top, again, to avoid the movement of any sand particles. I'm going to check the vacuum. All right, now that everything is pretty much in shape, I'm going to put the top cap on the specimen, and I am going to basically release. I need to hold the top cap, but I'm not pressing in so much, but what I need to do is to pull the membrane on the top cap to keep this all airtight. By the way, I did apply a little bit of vacuum grease to the top cap before doing this step so that the system is all sealed nicely. So there goes that. I'm going to pull the membrane just a little bit to make sure that everything is in good shape. Now the next step is to put this O-ring that I placed here on the top cap and actually do a second one on top of that. So here goes number one. So there goes that. And here's the other O-ring. So I have two O-rings now. And so what happens right now is that the system is under vacuum at the -5 psi that I had it originally at. But remember, what I need to do is I need to place this cell on top of this. But since this vacuum is connected, here's a side view of this. So what I need to do is actually switch vacuum from the bottom to from the side of the mold to the bottom of the specimen. So what I'll do is I'm going to turn on vacuum, keep it at the -5 that I'm at, and then I'm going to quickly release the vacuum from the side, and I'm going to hook it to this tube at the bottom that's coming through the bottom. All right, so I do that real quick. So there goes that. I'm going to still keep it at the -5. So I'm going to turn it off now. And so now vacuum is still on the system. We have full vacuum. But now it's going through the bottom. So now I can open up the mold. That's why we have this split mold. And there we have our nice specimen, which I'm going to turn around right now for you guys to see. So there goes our specimen. It's a pretty nice specimen. It's now stiff. It's under vacuum slash essentially effective stress right now. That's why the sand is all nice and stiff and sticking to each other, right? So if I actually press it, I'm not pressing it, but if I did, it's actually stiff and I wouldn't be able to easily crush it like the way they were before. Remember, this is what the sand looked like before, right? It was all just like beach sand. Nothing sticking to each other. But now that I applied the effective stress in the form of vacuum pressure, it's all nice and holding each other, forming a cylinder shape. So this is the step where I would measure the diameter of the specimen using a caliper, right? So you would do that at 3 locations. So at the bottom, you would make a measurement. You would make another diameter measurement at the middle, and then one at the top, because they may not be entirely uniform. And then for your calculations, you can use a average of the 3 measurements that I just did. And then for the height, you can use this side of the caliper to measure the height. Right, so this is what that would look like. Just showing you from the side, you would make a height measurement. So right now, the specimen is ready. It's under vacuum. Vacuum is being maintained. I'm actually periodically checking it to see if any vacuum is being lost. We don't want that to happen. So if that is happening, we would turn vacuum back on. I'm just going to clean this area where I have this O-ring, essentially my other seal for the acrylic tube, and placing that, because if I have some sand grains stuck in here, that is going to cause some air to go in and out of the system. So usually I would just clean it up, make sure there's nothing there. I would also clean the bottom of the acrylic tube right here to make sure there's nothing there either. Sometimes, because it's greasy, sometimes the vacuum grease tends to hold some of the sand particles, so we try to avoid that to have a perfect seal. So I'm doing that right now. Then I'm going to apply a little bit of vacuum grease again on here, just to give it a good seal. Don't necessarily have to apply vacuum grease if there is some there already, or you can just apply a little amount. So that's what I'm doing right now. Now is the time to place the vacuum grease. So I do that. If there are any sand particles stuck in there, you'll hear the sand. So that's that part. And then we have this little fence. This is for protection if by any chance the acrylic tube kind of breaks. You know, it doesn't let it shoot out or anything. Right, so the next step is to actually place this top portion of all this. This is what it looks like. This is the area where air can go in and out. This is where we connect the air pressure valve. So essentially you're going to consolidate the sample through this piece here. I'm going to place this on the top. And now's the time where we're going to apply these washers and pieces to tighten it up, the cell, and essentially make it airproof. So I have a couple of these. Okay. So now that we have the screws, I'm going to tighten it up. So just usually you would want to do like one round on each one and then go to the next one to apply the same amount of compression, and then tighten them all up kind of in order until they're all tight. So that's that. The last step is to add the loading piston on top of this system. Here you got to be particularly a little bit more careful, because remember, you're placing this on top of the top cap, and if you press too hard, then you're going to fail the specimen. I'm just going to do a check on the vacuum. Vacuum had gone down just a little bit from 5 to maybe 4 psi. I'm just going to turn it on to maintain the vacuum one more time. And remember, this is the vertical dial that is going to help me read off the vertical displacement, which later gets translated to axial strain. So I'm going to press this, but as soon as I feel a little bit of resistance, I'm also closely monitoring it. Once I have it in there, on the top cap, that is good. So the next step is to take off this system, and basically put it on the loading device, which I have right here. So what I would want to do,
Yeah.
okay, so this is what this looks like from a zoomed out kind of a view. So that is the load ring that we calibrated early on in the class, right? The load ring for the triaxial. And this is the triaxial machine, basically. So this little handle here is going to automate the movement of this bottom plate. So basically with time, this is going to rise up very, very slowly. And we'll have a connection right here from this loading piston to the load ring. Right now there's a little gap, but I'm going to fill it up. So I'm essentially going to bring the bottom all the way up so that this gets basically in close contact with the load ring. And with time, what's going to happen is that we're going to push this bottom up, right? And so what's going to happen is that this loading piston is going to fail the specimen, right? So the rest is of what you're going to see is basically that. But two dials here. So this is the displacement dial that you're seeing. This is particularly a little bit different with the other dials that you've seen in this class. It's a displacement dial, but the main principle is the same thing. So you have a small dial and you have a larger dial that is this bigger diameter reading that you're trying to do. And then we've talked about this one, which is the load ring dial, and how to calibrate it. So if you need to refresh on how this works, just watch the video on the triaxial load ring calibration. But the two main measurements during the test will be these two dials. So the vertical load from the load ring and the vertical displacement, right? And then the third person would be taking the measurements as the other two are making the readings. It's very important to know exactly what you're reading. So for example, in the load dial, everything is in 0.0001 inches. In the displacement dial, it's a little bit different. So every tick mark is 0.01 millimeters, as you can see, right? So it's important to know what exactly you are measuring so that the values that you capture later on make sense. Again, the system is still under vacuum. We haven't switched from vacuum to cell pressure, but we'll be doing that in a minute. I just wanted to give you a close-up of exactly what we're trying to do here. All right, guys, so I'm going to manually raise this plate at the bottom here with my hands, just to create that contact between the piston and the bottom of the load ring. As you read in the manual, if you don't create that contact and you apply the cell pressure, the piston can jump out and fly out, basically, which is not good, and we want to avoid that. So now that I have that perfect seal, I'm going to close this valve right here, because if I apply pressure, I want the air to get tight in here, not to go out. So I need to close this off. And the next step will be to connect this air pressure valve here. So the way that this works, I need to pull this out first and then press this in. You'll hear it make a click once it's fully closed. So now I am ready to apply the cell pressure. The first test is at 10 psi. The second test is at 20 psi, and the last one is at 40 psi. So I'm going to show you for a second, what this pressure dial kind of looks like. Remember, the system is still under vacuum, right? So the next step is to go essentially from vacuum on the specimen to applying air pressure. So what I'm going to do in this step is I already have my 5 psi of vacuum, so what I'm going to do is I'm going to, can you show this part? So I'm going to release the vacuum by unhooking this piece from the vacuum hose, and at the same time I'm going to apply the pressure here. Right now you can see that the pressure is reading, well, not great light here, but it's at 0. Right, so that's 0 right there. We're going to bump it up to 10 psi, right? So what I'll do is I'm going to release the vacuum and at the same time raise the pressure. So that's the vacuum released, and I'm going to go up to 10 psi. Can you show the right there? So there we go. That's 10 psi being applied on the specimen, and we've released the vacuum. So no more vacuum here. This is all open, and the view of this is pretty much the same as before. So the sample is holding each other, except the effective stress was first based on vacuum pressure. Now it's based on air pressure going into the system right here. So that's the air pressure going in, the 10 psi. We've closed it off, and we're ready to perform the test. So this is the step where I would need to face right here. I want to show this stuff. Let me actually come here. So this is the area where everything can be almost automated, right? So what I would want to do, remember, by moving this with my hand, this knob right here, I was able to raise the plate, and I was able to do that pretty quickly, actually. That was making a whole lot of displacement. So what I want to do now for the test is to switch it to some sort of automation, right? So in order to do that, I would need to push this knob in, which I will, but first I need to go to fine, and what that means is that it's going to make the movement of the plate very, very fine. When it's on coarse, that means it's going to move a lot faster. That's why I was doing it with my hand, but when I move to fine, that means the height of the plate is going to be raised very, very slowly in accordance with what it needs to be for this test. So then I push this knob and inside for the automated raising, and then the next step will be to turn on the loading, essentially. If I go right here where it says loading, that means that it'll start going up, right? So I would only do that when everybody's ready and in place. And when I say that, what I mean is, you know, one person is taking the initial reading from the vertical displacement dial. One person has taken the initial reading on the load dial, and everybody's in place. And you have a timer set up, right? You want to take readings every 30 seconds. So you want everybody to be in their positions and ready for the test to start. So with that and taking the initial readings, I'm able to turn on the test. And you'll see that the knobs are going to start moving automatically this time. And what this means is that this plate is being raised, right? So this is going up, but at a very, very low speed. You can't really see it with the eye. But once it starts going up, the dials are going to start moving. Usually, sometimes it takes a little bit, like 30 seconds, 1 or 2 minutes for everything to start moving in the directions they need to. So guys, sometimes what happens with this device is that you'll see this moving, but this one is still not moving. Sometimes it just takes a little bit of time for the machine to adjust to the gear, and whenever this starts moving, that's essentially when you want to start your time, right? Usually oh, there we go, just made a tiny little noise, and when that starts moving, the dials will also start moving. There you go. You can probably see the load dial kind of making some movement. Is this moving or not? Oh, there we go. So you'll see the displacement dial also making some movements. And this is when you would start taking your readings. Sometimes there's a little bit of false deformation that needs to be first captured with this vertical displacement, and then after that you'll see the load dial actually pick up and start moving. I think we're getting close to that. The load dial is also moving, not so much, but it's getting there.
Very slowly, but it is moving. Oh, there we go. I think it's almost picking up.
So this is when you would be taking your readings every 30 seconds of the load dial and the displacement dial. Guys, now that the sample has failed, I'm trying to show you a close-up, and if you can see that bulge in the middle of the specimen right there. So you had a perfect almost cylinder. Now you have a cylinder that's all bulged in the middle area, right? That means that the sample has failed, and we have reached to the end of the test. So we're going to take it all apart. So again, the first thing for taking apart the specimen and the testing is to first just release all that air pressure that we had applied, so go to 0 air pressure. The next step is to open up this top valve, make sure all the air is now released from the specimen. That's what you want to avoid. And then I open this, and what I'm going to do now is I'm going to bring down the plate manually, and now I can take off everything that I had. Mainly just put it back here, and the rest is to open up the specimen. If you can, it's always good to take all the sand apart and measure the weight one more time to make sure you have the correct amount of weight. This is the loading piston that I just took off, and basically that concludes the consolidated drain test on the dry sand. In the next video, I'll show you how to run the unconsolidated, undrained, or the UU test on a clay specimen. That'll be a little bit more fun.